Next topic is kernel and range of linear transformation. So this is the next topic, kernel and range of linear transformation. So definition is let uh, T from V to W be a linear transformation. Let T, right, T, capital T, colon v to W be a linear transformation where V and W are vector spaces. Then kernel of T is denoted by this notation KRT or KT, just K in bracket T, capital T, and is defined as kernel of T is equal to V bar belongs to V or V belongs to V, that is the elements from this domain such that TV is equal to 0 bar or TV bar is equal to 0 bar. That is the image whose images are 0 are the vectors of kernel of T. Obviously, this kernel of T contains 0, 0, 0 vector, that is 0 bar vector, because T of 0 bar is 0 bar for any vector space V. And so kernel of T contains at least one element that is 0 bar, because T of 0 bar is 0 bar. We know the property of the linear transformation that T of 0 under linear transformation T of 0 bar is 0 bar, under which the function, if T of 0 bar is not equal to 0 bar, in that case T is not linear transformation. So this set contains at least one element. For any example, kernel of T contains at least one element, that is 0 bar. That is, kernel of T is not never no empty set, is always non-empty set for any example. So, and it is subset of this capital V, that is domain of the linear transformation. T is a function from right like this here, T colon V to W, right here, T colon V to W. So T is a linear transformation, and therefore kernel of T is subset of domain, its domain, that is subset of V, and this set contains the element from V, that is the elements of V under such that T of V bar is 0, that is whose images are 0 bar, then we say that elements belongs to kernel of T. So the range, and the next definition is the range of T is denoted by RT, denoted by RT. The notation is this RT, and is defined as RT is equal to W bar belongs to W. That is, the elements in RT comes from this codomain of the linear transformation from W, this capital W. So if the element W bar belongs to W, such that there exists some vector V bar in V, V bar in V, that is domain, such that TV bar is equal to W bar. That is, V bar is pre-image of this W bar. That is, the element of W which are images of some element of V belongs to this RT. That is, RT contains the all images. That is, RT is the set of images. Indirectly, we know that what is the set of the image set of the function. We know that this set is the subset of this codomain, this RT, and is the set of all images under T. That is, this is the set of W from W, this capital W, such that there exists some vector, at least one vector V bar in V, such that TV bar is equal to W bar. That is, the image of that V bar is W bar. That is, the V bar is pre-image of this W bar. That is, W bar is image of some element of V. That is the RT is this is the definition of RT, range of T. It is the set of all images. That is, if the element belongs to RT, then it is image of some at least one element from the domain. That is, it is the image of some element from domain. Otherwise, the element does not belongs to RT, which are not images, are not the elements of this RT. So this RT is subset of this W codomain. So kernel of T is subset of domain of that linear transformation, and range of T is a subset of codomain of that linear transformation, that is W. And the theorem is prove that T is from V to W is linear transformation. Then prove that kernel of T is subspace of this capital V, and our range of T is subspace of W. So we have to show first kernel of T is subspace of V, and obviously kernel of T is what is a subset of V, and kernel of T is not equal to phi, as 0 bar belongs to kernel of T. At least one element belongs to kernel of T, and therefore kernel of T is not equal to, is not empty, is not equal to phi. So these are the two basic conditions of the subspaces. Then and what is the definition of kernel of T? Is the element set of elements from V, that is V bar belongs to V, such that TV bar is equal to 0 bar. That is, this set contains the element from the domain of the linear transformation whose images are 0 bar. That the elements which maps to 0 bar are the element of this kernel of T. So kernel of T is subset of V, and kernel of T is not equal to phi. So this sentence is directly, obviously, or directly we say. So this is the repetition of topic subspace. So how we can show the subspace? We show the two conditions. What are that two conditions? Show the set is closed for addition, and show the set is closed for scalar multiplication. That is, addition of every two element of kernel of T belongs to kernel of T. What we have to show in the first condition, in order to show kernel of T is subspace of V, we have to show two conditions. What are that two conditions? First, take the two elements from kernel of T, be any vector. Suppose V1 bar and V2 bar belongs to kernel of T, be any vector. And what do we have to show? We have to show V1 plus V1 bar plus V2 bar also belongs to kernel of T. So as V1 bar belongs to kernel of T, by using this property of kernel of T, T of V1 bar is 0 bar, and V2 is also element of kernel of T, and so T of V2 bar is 0 bar. And now we have to show V1 plus V2 belongs to kernel of T. So when V1 plus V2 belongs to kernel of T, if T of V1 plus V2 is equal to 0 bar, so consider T of V1 plus V2 bar, then what is it is equal to TV1 plus TV2 by using linear properties of linear transformation. So there are two properties, basic two properties of linear transformation, that is TU U plus V is TU plus TV. By using that property, we have T of V1 plus V2 is equal to T of V1 plus T of V2, and T of V1 is 0 bar, T of V2 is 0 bar, and 0 bar plus 0 bar is 0 bar, and therefore V1 bar plus V2 bar belongs to kernel of T, because V1 T of V1 bar plus V2 bar is equal to 0 bar, and therefore this V1 bar plus V2 bar belongs to kernel of T, and therefore we say V1 bar plus V2 bar belongs to kernel of T for all V1 and V2 belongs to kernel of T. This is the first property. Now we take any vector from kernel of T. Suppose V bar belongs to kernel of T, or take V1 bar as a element of kernel of T. So take V bar as a kernel belongs to kernel of T, and K be any scalar. Now we have to show K into V bar belongs to kernel of T. As V bar belongs to kernel of T, therefore we have T V bar is equal to 0 bar. And now we have to show K V bar belongs to kernel of T. So when K V bar belongs to kernel of T, if T of KV bar is equal to 0 bar, then we say KV bar belongs to kernel of T. So consider T KV bar is equal to KTV bar by using the property of linear transformation, second property of linear transformation. T KV bar is KTV bar, and then K and TV bar is 0 bar. So K into 0 bar is 0 bar, and therefore KV bar belongs to kernel of T. Why K into 0 bar is 0 bar? Because of the property of vector spaces, vector space. Okay, so there are 10 properties of vector space. Out of that, this is the one property, K into 0 bar is 0 bar. So KV bar belongs to kernel of T, because T of KV bar is 0 bar, and therefore KV bar belongs to kernel of T. And therefore we say KV bar belongs to kernel of T for all V bar belongs to kernel of T, and for any scalar K. As this V bar is and K are any two elements, and the property is true for any two element, and so we say the property is true for all element, and hence kernel of T is subspace of the vector space V. So kernel of T is subspace of vector space V. So right here the sentence, therefore kernel of T is subspace of V, right, of V. Then we have to show the range of T is subspace of W. So what is the definition of range of T? The range of T, the definition is, right, first definition of range of T, that is the range of T is this T from T is from V to W by linear transformation. The range of T is what? W bar belongs to W, that is the elements from W, such that there exist, right, hence not hence, there exists some vector V bar in V, capital V, such that TV bar is equal to W bar. That is, this W bar is image of some element of capital V. So this is the definition of RT, and we have to show RT is a subspace of W. Clearly or obviously, RT is not equal to phi, and RT is equal to RT is subset of W bar. Why RT is not equal to phi? Because 0 bar belongs to RT, because T 0 bar is what? 0 bar. So 0 bar has pre-image, and so 0 bar of this W belongs to RT. So write directly that clearly the set is not equal to phi, and the set is subset of this W. RT is subset of W. Now we have to show the two basic conditions of subspaces. First condition is what? We have to show RT is closed for addition, and then in the second property we have to prove RT is closed for scalar multiplication. Let W1 and W2 belongs to RT be any elements. Now we have to show their addition also belongs to RT. But as W1 is the element of RT, and W2 is the element of RT, this W1 and W2 are has pre-images because of this definition. That is, therefore there exists two vectors V1 and V2. Say its notation, we can take another notation also, U1 and U2, or any another notation. So there exists some two vectors V1 and V2, or V1 bar and V2 bar belongs to V, such that TV1 bar is equal to W1 bar, and TV2 bar is equal to W2 bar. Okay, TV1 is equal to W1 and TV2 is equal to W2. This bar is not essential. We either write this bar or without bar, these elements. So W1 and W2 are the element of RT, and so it has pre-images. V1 and V2 are the supposed two pre-images of this W1 and W2. And now we have to show this W1 plus W2 belongs to RT. When W1 plus W2 belongs to RT, if W1 plus W2 is image of some element of V, capital V. So consider T of V1 plus V2 is equal to TV1 plus TV2, as T is linear transformation, and TV1 is W1, TV2 is W2. And so what do we have? That T of V1 plus V2 is W1 plus W2, that is, and V1 plus V2 is the element of V, as V is a vector space, and W1 and W2 are the element of V. So their addition also belongs to V, because the first property of vector space is what? That vector space is closed for addition. Addition of every two element of vector space belongs to vector space, and therefore V1 plus V2 belongs to V, and therefore this W1 plus W2 has pre-image in capital V, that is, V1 plus V2 is the pre-image of W1 plus W2, and therefore W1 plus W2 belongs to RT, because it has a pre-image, and therefore we say that W1 plus W2 belongs to RT for all W1 and W2 belongs to RT. The property is true for any two element of the RT, so we say the property is true for all elements of RT. Then next property, let W bar belongs to RT be any vector and K be any scalar. Then we have to prove that this K into W bar belongs to RT. So as W bar belongs to RT, there exists some vector, suppose V bar, say V bar in V, such that TV bar is equal to W bar. That is, this W bar belongs to RT, means W bar is image of some element of this capital V. So that is, suppose that element is V bar, that is TV bar is equal to W bar. Image of this V bar under T is W bar, suppose. Then consider T of KV bar. Then it is K into TV bar by using property of linear transformation, as T is linear transformation. And K and TV bar is W bar. And so note that, and this KV bar belongs to belongs to V, because V is a vector space. And the second property of vector space is what? The vector space is closed for scalar multiplication. That is, any scalar and any vector, that multiplication belongs to that vector space. So KV bar belongs to V bar, because K is any scalar and V bar is the element of V. So their multiplication belongs to V bar. And therefore, this KW bar has pre-image in capital V, that is KV bar. the image of kv bar under T is kw bar, and therefore kw bar belongs to RT, and therefore we say kw bar belongs to RT for all w bar belongs to RT and for any scalar k, and hence RT is a subspace of W. Hence RT is a subspace of W because RT satisfies the two conditions. So now we will see the examples of kernel of T and range of T. Before that, we have to write the function in the form of the matrix, linear transformation in the form of matrix. So we have already seen that how we can write the function in the form of matrix, or how we can find the standard matrix. So this is the procedure to obtain the standard matrix. So the example on this kernel and range of T. So here is the definition of nullity of T and range of T. So what is the nullity of T? The dimension of kernel of T is called nullity of T and is denoted by this notation NULLITY T or NULL in bracket T, nullity of T. And the dimension of RT, the range of T, the dimension of range of T is called rank of T and is denoted by this notation RANK, rank of KT, rank of T. So rank of T is what? Rank of KT, rank of RT. So rank of T is denoted by this RANK in bracket right T. So dimension of range of T is called rank of T. Right here is note, let T be a linear transformation represented by matrix A, that is Tx is equal to X. That is A is the standard matrix for linear transformation T. Then kernel of T is equal to null space of A, and the range of T is column space of A. So in order to find the range of T and kernel of T, linear transformation, kernel of linear transformation and range of linear transformation, we have to write the linear transformation in the form of matrix. Then we have to find the standard matrix, and now the null space of that standard matrix A is kernel of T, and the column space of that matrix, standard matrix A, is a range of T. And it's very easy now to obtain the null space of the matrix A and column space of the matrix A, because in the previous topic we have already seen that how we can find the dimension and basis for null space of the matrix A, any matrix A, and the column space, basis and dimension of column space of any matrix. So null space of A, we know that null space of A is the solution space of the system Ax is equal to 0. And how we can find the basis and dimension of column space of A? This is the reduce the matrix A to its echelon form, not echelon form, reduced row echelon form. And the non-zero rows form the basis for row space of A. The non-zero basis for row space, non-zero rows forms the basis for row space of A. That is, if you reduce the matrix A to echelon form or a row echelon form, then the non-zero rows in its echelon form form the basis for row space of A, and the corresponding columns in A that corresponds to columns contains leading one in row echelon form, row reduced row echelon form, forms the basis for column space of A. So how you can write the basis for column space of A? The corresponding columns in A that corresponds to columns contains leading one in reduced row echelon form, correction is here, reduced row echelon form, forms the basis for column space of A. That is the, suppose the we obtain the reduced row echelon form of the matrix A, and suppose the column number 1, 2 and 5 contains leading one of the reduced row echelon form. Then the corresponding columns number 1, 2 and 5 forms the basis for column space of A. Already we have solved such a type of example, that is, find the basis and dimension of null space of the matrix A, find the basis and dimension of row space of the matrix A, find the basis and dimension of column space of matrix A. So we know that how we can find that the basis for a row space, column space, null space of any matrix. The column space of A is a row space of A dash right here, A transpose. The column space of A is row space of A raised to T right here, A raised to T, A transpose. That is, if you have to find the basis for column space of A, we can obtain the basis for row space of its transpose, A transpose. Then it is a basis for column space of A. So the column space of A is the row space of A transpose. How we can obtain the transpose of any matrix? Write the first row as the first column, second row as the second column, third row as the third column. In this way, interchanging the rows and column, we get the transpose of the matrix. So we can also use this method, this note to obtain the column space of matrix. Either use this note to obtain the basis for column space of matrix, or use this matrix, use this method or note to obtain the column basis for column space of A. That is write A transpose and obtain the basis for row space of A transpose, and it is a basis for column space of the matrix A. So this gives the another method, or we can obtain the basis for column space by using this method. Because if you have to obtain the basis for range of T, RT, then we have to obtain the basis for column space of T. So how we can obtain the basis for column space of A? By using this note. That is reduce the matrix A to reduced row echelon form, and then note the note the columns that contains leading one, and the corresponding columns in the matrix A forms the basis for column space of that matrix A. And in order to or we can obtain the basis for column space of A by using this method. That is write A transpose and then obtain the basis for row space of A transpose, and it is a basis for column space of A. And how can obtain the basis for row space of any matrix? Reduce that matrix to echelon form, and the non-zero rows in the echelon form form the basis for row space of that matrix A. So the question is find rank and nullity of T, or the question is find basis and dimension of kernel of T and range of T, or find kernel of T and range of T. So all the questions are having same answer, same procedure. That is, in order to find rank of T and nullity of T, what is the rank of T? Rank of T is the dimension of range of T, and nullity of T, rank of T is the dimension of range of T, and nullity of T is what? Is the dimension of kernel of T. So in order to find rank and what nullity of T, we have to find the dimension of range of T and kernel of T. And in order to find dimension of kernel of T and range of T, we have to find the basis and dimension of kernel of T, basis of kernel of T and range of T. In order to find the dimension of kernel of T and range of T, we have to find basis for kernel of T and range of T. So what is kernel of T? The kernel of T is a null space of A, and range of T is what? Is column space of A. So we have to solve this example. And so what is the procedure to obtain this answer of this example? So we we will find the matrix A, that is the standard matrix of linear transformation, and then find the dimension, basis and dimension of null space of the matrix A, and then find basis and dimension of column space of A, or find the basis and dimension of row space of A transpose. So this is the very simple procedure to obtain the rank T and nullity T. So this is again the repetition of the previous topic, that is the null space, row space, then column space of the matrix. So this total topic depend on the previous topic, that is the dimension and basis of null space of matrix, row space of matrix, and column space of matrix. So we will solve this example in the next lecture.